Now, I'd like to introduce us to Raul from Barcelona. So, Raul, would you like to turn your camera on and your microphone?
Hello, thank you for having me.
Hi, Raul.
Hello,
Very nice to have you.
it's an honor. Thank you very
Yes,
much.
very awesome. Raul, would you be able to tell us a little bit about yourself? Like, what are you studying and why you wanted to go into physics?
Yes, so I am studying physics, as you mentioned, and I've always had a passion for it. Um, I find that there's meaning in understanding reality, and when you want to understand the world we live in, physics would be the first chapter of the book. And I find it fascinating that there's a book to start with, and there's no author, and I really find it mesmerizing when or profound when you learn physics. So I've really been gravitated towards it from the start.
Oh, that's fantastic. We love being passionate about what we do because it just makes the work so much better too. Would you be able to tell me about your experience at the university you're currently at? Do you enjoy it?
Yes,
What have you liked about the course that you're doing? The research in particular, I see is very interesting. Would you like to give
yes,
us a brief on that?
of course, yes. I've been studying at the University of Barcelona here, where I'm located now, and I have, during my study, have gone abroad recently to on exchange to Australia. And there I was able to take a research project. I'm now continuing here, and I've enjoyed very much my study in physics. I'm now in my fourth year, just finished it, made lots of friends, and yeah, it's a great experience. I really, really would recommend it to everyone. Yeah.
Oh, that's so good. We love the Aussie Down Under experience too. You get to see all the kangaroos
Yes,
as you do all your
lots of
work.
wildlife,
So that's
lots of
amazing.
wildlife.
What lots of wildlife, yeah. So if for any viewers are looking for their next holiday destination, come down to Australia. We have some really good wildlife. We've got good kangaroos, koalas. Just don't get bitten by any of the patterned like animals, and you're good to go. So I would highly recommend a
Yeah,
trip to Australia at some point. Okay, Rao. So it's your time. Would you like to share your screen and
sure,
introduce what you're doing and what you'd like to talk to us? Thank you.
perfect. So I'll just share my screen quickly here. Let me know if you can see this properly.
Yep.
Yeah,
Yep.
fantastic. So I'm just going to minimize here my face. Okay, perfect. So thank you, Ashley, for introducing me. Again, it's an honor, and thank you everyone for coming to listen. I was going to say we'll do a seminar here as always, and we'll do a Q&A session at the end. And throughout, there'll be slides that have poll questions. So hopefully it'll be a bit more engaging with the audience. And yeah, so I think if you have any questions, feel free to text in the chat. I'm sure Ash can direct them to me in the Q&A session. And if you have any follow-up questions, you can email me here. This is my email. And yeah, I think we can start now. So today we'll be talking about the cosmic microwave background, which I'm sure you've all heard of, and we'll be talking about it and how it's a probe for cosmological model testing, in particular, how we can look into the fitting of some parameters such as the curvature of space. So before going into details, I wanted, since this is a iTelescope webinar, I wanted to start off with a more like didactic kind of story from the astronomer's perspective. So imagine that, let's see, we've got here, there you go. Imagine that you've got a very strong, powerful radio telescope, and one night you choose to aim it at a patch in the sky which is completely dark, has no galaxies, no stars, and you aim it at this patch. Initially, what you'd expect to see is nothing. You'd expect to see complete darkness. But in fact, however, you do see a faint glow. So what you see, if you plotted it on a computer, if you collected data from all directions in the sky, what you'd see would be something like this. This is quite a boring picture. It's quite a uniform radiation that you'd see from all directions. And I've mentioned here temperature. Just remember that all objects, just by being at a temperature, emit radiation. So conversely, any radiation we can see, we can interpret it as it incoming from a body with a given temperature. And this thing that we see is remarkably boring. It's the same kind of glow everywhere we look. We see this kind of glow, and it's not associated to any object in the sky. It's not a galaxy, no stars, nothing. So, by the way, if you're wondering why the shape, why it's this elliptical shape that we're looking at, this is basically a projection of a sphere onto a plane. So, a very common example of this would be this map, which we've all seen. And it's the same thing, just that in our case, instead of looking down, we'd be looking up. So we have this very faint glow in all directions again, which is very uniform. And if we turned up the scale, so if we increase the contrast, what we'd see would be a bit more interesting. We'd see something like this, what's seen in the second image. Here, again, temperatures are represented by color map. So high temperatures would be red, low temperatures would be blue, sorry. And we see that there's more variation now. This variation, however, isn't the cosmic microwave background that you've probably all heard of. This is more a relic of the Doppler effect. So since we're moving, since we have a particular velocity with respect to the cosmic microwave background, incoming rays get blue shifted and red shifted depending on the orientation that we have with respect to the radiation when we move. So if we take out this anisotropy we call, this like lack of symmetry under rotation, if we take this out and we subtract the dipole, what we get is something like this. So this again isn't the cosmic microwave background. It is in fact the Milky Way, what we're seeing. Since we're living in the disk of the Milky Way, we see it as a straight line. It's like a plane. And again, this isn't the cosmic microwave background. This is mainly radiation emitting from the Milky Way. So again, subtracting the Milky Way emission, what we see is now finally the cosmic microwave background, which is very commonly abbreviated CMB. And this cosmic microwave background has an average temperature of about 2.7 Kelvin. So it's very, very cold. It's only a couple Kelvin above absolute zero. And remember, Kelvin, with respect to Celsius, it's shifted about minus 270 degrees. So this would be roughly around minus 270 degrees Celsius. So it's a very cold radiation. Again, this would be the temperature associated to the radiation we see. Again, this is a zoomed in version. And we see red patches, blue patches. Red would be hot spots, blue would be cold spots. And these anisotropies, these fluctuations that we see, are very important. They are said to be the seed that then gives rise to large scale structure that we see today. So all the galaxies, the clusters, etc. So now I'll start off with my first question, which is, how large are the relative temperature fluctuations with respect to the mean temperature of the CMB? I'll let everyone answer and see what their guesses are.
Okay, we'll give Raul will give them about a minute or so. Okay, so you
Of course, yeah.
can't see, but
I should
people
be
are,
more patient.
yeah,
Sorry.
they're answering. Just I'll go whilst they do that. I'm going to throw in a very quick question because I'm more an experimental.
Yes.
I think this is fascinating. What you're doing there is with the subtraction actually. So how can we be so sure that when we measure our Milky Way and so on, that really what we're doing there in the end
Yeah.
is really the signal from out there, right? And it's not by
Yes.
local thing. How can we be so sure it is like that?
Yes. Yeah, that's a great question. And obviously, there's different degrees of data processing. You can go in more in depth or less in depth, and it depends on what assumptions you make. Some assumptions are more approximate and some are more strict. Um, Mainly, one thing that helps quite a lot is that you can take several surveys of the same sky, and whereas noise is uncorrelated with each other, you'll get the same CMB signal on both surveys. So you can play with
Good.
this the fact that CMB signal is
That's a good
correlated with
answer.
itself.
Thank you. Thank you. That's a good
Yeah,
answer. Okay, here you go.
perfect. Okay, so I see the majority have voted for option E. And congratulations, yes, that is the right answer. These fluctuations are really small, so they are of the order of 1 part in 100,000. And this is with respect to the temperature. So temperature is a small temperature, but the fluctuations relative to this mean is a very small fluctuation. Nevertheless, as we've said, it's very important towards cosmic evolution and formation of large-scale structures. We'll move on now and just talk about some more facts of the cosmic microwave background. So as we mentioned, it fills all space in the observable universe, so not only where we stand, but in all points of space, there's rays traveling in all directions. And this CMB originates from a very young universe, only 380,000 years old, about. And it's, if you'd like, the smoking barrel of what is the Big Bang. So it's a landmark evidence of the theory of the origin of the universe. Can maybe, like in the analogy of the gun, you could say that from the smoking barrel, you can infer that the gun was shot. And it matches a perfect black body. So it's a very, very good black body. It has a very good black body radiation curve spectrum that matches perfectly with theoretical predictions. And it's a very good probe to test cosmological models. And as we mentioned now, and as you all, majority of you guessed or knew, the temperature variations are very small. And the CMB is considered to be, when doing cosmology, statistically homogeneous and isotropic, and a single realization from a random Gaussian field. So one thing that's very common in cosmology is that we can only see one universe, but maybe the model that we use assumes the distribution from which this universe is only a sample of. So we assume that this distribution from which the CMB is just one realization is a distribution that has statistically homogeneity, isotropy, and it's a random Gaussian field. These properties, in particular the fact that it's statistically isotropic and Gaussian, make the whole analysis of the CMB much more simplified. It makes it incredibly simplified because instead of having to predict the fluctuations of each patch in the temperature map of the CMB, all information can be compressed without any loss of information into what is known as a single function known as the angular power spectrum. Now, this angular power spectrum represents the variance of temperature fluctuations as a function of scale. Now, for any of you who have heard of Fourier transforms, it's quite a similar thing to a Fourier transform. A very common problem in engineering is signal processing, where I won't go into depth, obviously, it's not much time, but the main idea is that from a complex signal, we can decompose it into its building blocks that are more simple. And by taking a Fourier transform, we can see which building blocks are weighted the most, which are most dominant in the original signal. So in the cosmic microwave background, we do a similar thing, just that instead of the function in which the signal lives is a flat space, instead of the function living in a flat space, we're now decomposing this function in a two-dimensional space that has curvature, a sphere. And also, this function isn't of time, as on the left, it's of angular coordinates. So that's also a subtle difference. And the building blocks that we'd use to then make this complex signal before was sine and cosine waves. Now it will be slightly more subtle. It will be spherical harmonics. but the same idea applies more or less. And the again, the graph in blue on the left would be the equivalent of the power spectrum, the angular power spectrum on the right, which would tell us once again the temperature variations that they are as a function of angular scale. So here comes another question, and that is, by looking at the angular power spectrum of the CMB, what is the characteristic angular scale of temperature fluctuations? We'll give it another minute and we'll see what everyone says. This one may be a bit harder if you haven't heard of it before. You can look at the graph for any help. On the bottom, you can see angular scale in the horizontal axis. Temperature fluctuations are in the vertical axis. Okay, so this time we have a more sparse voting. The majority, 44%, have said option C. That is around 0.1 degrees. And we have quite a varied result amongst all of us. I think 22% have answered option 1, 11% option B. Okay, so this was a bit of a more subtle question. Again, can you see my mouse, by the way, Ash? I was wondering.
Yes, we can see.
Yes? Ah, perfect. That's very useful. So then, remember that angular scale would be this horizontal axis. And similar to before, when we saw, by the way, the right answer is option B, 1 degree. Similar to before, when we saw this graph here that showed us which was like the main building block that would have more weighting on it within this original signal. The same thing happens in the angular power spectrum. So here at 1 degree, we can see that we have a peak, it's the highest peak, and that would mean that the majority, the characteristic angular scale of temperature fluctuations happen at 1 degree. For a more, I guess, visual way of remembering this, 1 degree is about the width of your pinky finger if you stretch it at arm's length. So you can imagine more or less having your pinky finger at arm's length, and then the width of that would be the angle at which the majority of these temperature fluctuations that we see in the cosmic microwave background radiation appear. So that would be more or less a visual idea of what we get. So now we'll move on and we'll talk about the cosmic microwave background as a probe of cosmological models. And in particular, we'll talk about one parameter we could more or less look into, which would be spatial curvature. And to start with, I think it's worth just asking the question. This time you can answer in the chat if you like. What do you think it means for our universe to have a curvature to start with? Because sometimes that even sounds weird in itself. We'll see what everyone has to say. So, Ash, can you see in the chat what
Yes,
been
I
said?
can see the chat, but nothing's been said at the moment. There's been one comment that the displayed question before was a bit different to the one on the slide, though.
Okay. I hadn't read it through all of them. I assumed they were the same.
Okay. I guess we see how people have answered it. It's fine. Okay.
So then
In the
I'll just minimize this quickly and go ahead with the presentation. So then I guess the most common way of thinking of curvature in space is the one that it's on the covers of all the general relativity books. And that is that energy and mass warps space-time, and that space-time then dictates how objects in the space have to move. However, in cosmology, we usually look at much bigger scales. So these kind of curvatures that we see here in this image are just local and just small ripples of the actual global cosmic scale. So then when we look at curvature in cosmology, we refer to a more global notion of curvature, a more global geometry of the space. So we'll just have a very simple example here to start off. We'll start with two observers, and we'll now go down to 2 dimensions, and then we'll extrapolate to 3 dimensions once again. So then we'll imagine these 2 observers live in 2 universes, which we'll name A and B. And these 2 observers live in 2 dimensions. However, it's very clear that even though they live in the same dimensionality, the spaces are just by nature very different. They're intrinsically different. One is curved and one isn't. And from our point of view, this seems very obvious. But if we extrapolated to 3 dimensions, we wouldn't really be able to tell what that would mean instantly, because what we're actually doing here in this simplified case is having an advantage where you can see these 2 spaces from like a God's eye view. You can see them from a bigger dimensional space. So we see these 2-dimensional spaces embedded in a 3-dimensional space. And that allows us to see very clearly which one is curved and which one isn't. But for these 2 observers, it's not that simple. And you can imagine, for example, if I got a mouse and I put it here, my mouse, neither observer can see my mouse. If I put the mouse on the sphere, the observer that lives within the surface of the sphere will be able to see it. And vice versa, if I put it on the surface of this infinite plane that you could imagine of universe B, well, the observer would be able to see it. But outside, they can't see it. So one interesting question to ask is, how can these observers tell if they live in a curved space or not? Since that will be actually the problem that we will be in when we extrapolate this to 3 dimensions. So again, I may just leave a couple of minutes just to see what the chat has to say, if someone has an idea of what you could do to verify from the point of view of these observers, whether you're in a curved space or flat space. Okay, I see some people have already very, very educated guesses already. Somebody has asked, has suggested using triangles, which is a very good idea. And I've seen also a comment on the path light takes being straight or not. So then that's good, good answers. Let's see here, I'm going to just click on here. So the idea of using triangles is a very good one. And light, again, as mentioned in the chat, will take different paths. The question whether it's straight or not is more subtle, because what is a straight line in a curved space? You have to generalize the definition, I guess. But using triangles is a very common method to, well, not very common method, but a very good method to see in which kind of space we are. So then if we draw a triangle in a sphere, we would have that the edges of this triangle are slightly beveled, and this would increase the interior angles of the triangle. Whereas in a flat space, the triangle in the Euclidean flat space would have an interior angle that would sum up all 3 of them to 180 exactly. So then, as mentioned in the chat, this is a good way of checking. And in the case of a sphere, you'd have more than 180 degrees. In the case of a flat plane, you'd see 180 degrees. There's a third case that I haven't mentioned, which would be in negatively curved universe, where the sum of the interior angles would be less than 180 degrees. Now I've got another question, which is, are there any problems with this method? So imagine we go out, we tell these observers, just draw a triangle. Are they going to encounter any problems? Or will they be able to figure out immediately the curvature of the space they live in? Okay, I've seen also someone's mentioned walking a straight line will return you to the same point in the sphere. which doesn't happen on a plane. That's a good point. So you could cross and travel all the circumference of the sphere and come back to the same point. Yes, so as mentioned in the chat, one of the problems is to be able to recognize the curvature of the space you are living in. The size of the triangle has to be comparable to the curvature of the global space you're in. So then this triangle, for example, here on the left of the sphere is a very big triangle if the whole sphere would be the universe. So you need a very big, very, very, very big triangle. And locally, the effects of curvature aren't really that noticeable. A good example would be Earth, for example. So on Earth, we know it's a ball, but on the surface, locally, everything looks quite flat. When you travel to a supermarket, you don't consider, I'll have to dip into the curvature of the planet. You don't think about that. And it's actually so good, the illusion that it's flat, that some people may even believe it's flat. So locally, you can't test easily the curvature of space, and you need a very, very big triangle. So that's where the CMB comes in the search of a very, very big triangle in the end, something similar to a big triangle. So the way that the CMB is dependent on the curvature is defined by how light rays coming from the CMB are affected by curvature on their path all the way to us. So if we have a flat space with no curvature, if all the grid lines in the coordinates are all parallel, we will then get a triangle, which we can see here, where the patch of some fluctuation of temperature could be the base of the triangle, and then the two equal sides of the isosceles triangle would be the light rays that travel towards us, forming an image in our pupil or in our telescope. And we would see a certain size that would be, well, the real size of patches in the CMB. However, if we have positive curvature, if we are living in a sphere, like a kind of universe, then the light rays that are parallel end up converging always. So that means that the light rays that before converged to our eyes now will converge too soon. And by the time they reach our eyes, they'll be already divergent. They won't form an image. So rays that do form an image in our eyes are actually ones that start off slightly pointing outwards. And when they converge into our eye or telescope, we end up with the apparent size of a patch that is larger than the original. So we see an increase in the patches in the CMB. Similarly, in negatively curved spaces, lines that are initially always parallel end up diverging, and lines that are converging sometimes diverge too. So what you'd need is to have, they always diverge. So then instead of having the same case as the beginning here with the zero curvature, the lines that were of zero curvature that would converge to our eyes would diverge by the time they reach us. So we'd have to start off with rays that are pointing further inwards, and that would only converge when they reach us. So this would give us the opposite effect. It would give us the effect that the apparent patches of temperature fluctuations in the CMB are actually smaller. So in this sense, the CMB is very highly sensitive to the curvature of space. And that makes the CMB a very good probe to then determine the curvature of space. Now I'm going to do a quick question. Just before I do the question, I'm going to do a small recap of what I've just said. Just as a takeaway note, if the curvature is null, we see a certain size in temperature fluctuations. If curvature is positive, these fluctuations are bigger than what they really are. And if the curvature is negative, they become smaller than what they really are. The shape of the fluctuations don't change, it's just the scale. So now the next question is, how does curvature affect the CMB angular power spectrum? So take into account what I just said, just changes the scale. So option A, it shifts the spectrum horizontally. Option B, it shifts the spectrum vertically. Option C, stretches or compresses the horizontal axis. And option D, it rotates the whole spectrum.
I think that was the one, Raul, that I
Yeah,
put in. I think
that's
that's
the
where the
one.
confusion comes on because I think you had three and I only thought you had two. So that's my,
Ah, sorry.
I didn't know that. Okay. Okay.
Sorry, that's my
Yeah.
fault then.
No, no, don't
I'm
worry
sorry
about
about the
it.
confusion.
It's but thanks to someone who pointed it out. So sorry for the confusion.
Well, we can look in the chat if not, I guess. See if they say A, B, or C, or D.
Yeah, let's write our answers in the chat, guys. A, B, C, D, what you think it is.
Okay. You can tell people are thinking. They're not typing instantly the answers, but slowly the answers are coming. Okay. So then the right answer is, let's see if we can click it here, option A. So since the angular scales are increased or diminished, this shifts the peaks left to right and right to left, depending on how you tweak the curvature. So remember that the horizontal axis on the angular power spectrum is representing or quantifying angular scales. So at the left of the horizontal axis, we have very big angular scales. To the right, at the end, we have very small angular scales. And the amplitude of the curve is telling us how much temperature fluctuations there are in those scales of angle. So if we make the curvature positive or negative, it shifts the whole peaks right to left because it changes the scales at which we see them, but it doesn't change the actual shapes or the temperatures that we see. So then here's a more visual representation of this. So you can see here how the curve shifts left to right, the amplitude is conserved. There's some subtle effects happening at big, large angles, but on the peaks, generally, it's just shifting left to right. So shapes are not changed, values are not changed, it's just the angular scale that we see them at. So now I'm just going to move quickly to a quick overview of what CMB data analysis would look like if you did it at home. There's many places online where you can download CMB data and you can play with it and analyze it. If you did that and you plotted the power spectrum immediately, what you'd get, it would be something that looks like this on the right. Ignore the axis, is more or less, it's the same thing as before. We're just using different quantities. Before, on the horizontal axis, we had angular scale in degrees. Now we're using a different quantity. It's called the multiple moment, L, which is something to do with the spherical harmonics, but again, it just represents angular scale. And as you can see, we don't get the smooth curve we saw earlier. So there's several reasons for this. And when you're doing data processing, you've got to account for these possible factors that are influencing your data. So even in data that is given by very well known missions and surveys, there is always some foreground emission. So you can download the data, but within the data, you'll see always that there's some residues where the cleaning function didn't quite work. So you'll see some blurry patches in the cosmic microwave background in that elliptical map. And those blurry patches will always have to be blurred out, or not blurred out, but masked. That would be the word. So you have to take them, subtract them off the map so that they don't influence or bias your estimations. And on the other hand, you've got instrumental noise. That is more of a common feature of measurements. You can imagine where that would come from. It could come from electronic noise, etc. Then we've got beam. At the end, we've got beam window functions and pixel window functions. This is a fancy name. Just take away from this that from the fact that the whole image is pixeled, it isn't an infinite resolution, and from the fact that when you measure with a telescope, you're doing convolutions on what you're measuring. The fact that these processes are happening also biases your estimations, and you have to compensate that too. And the more exotic kind of source of error or problems is cosmic variance. This is something that's more only seen in cosmology. You don't see these kind of errors, this type of error in other fields of science. This is due to the inherent fact that we only live in one universe. So due to the fact that we only live in one universe, we only see one realization of the underlying distribution that generates the cosmic microwave background. So cosmic microwave background is just one sample of this distribution. So it's like if you roll the dice and you only can see one face of the dice because you just live on one face of the dice. It's a bit of a rough analogy, but more or less that's the gist. And a quick overview of what you do to fit parameters would be, on the one hand, you'd have observed data. You'd want to process all the data to clean all of these sources of error that I've mentioned now. And on the other hand, you have a model prediction. So you'd have a set of parameters in your model, and one of them could be the curvature, for example. And with this set of parameters, you should then calculate the corresponding associated power spectrum, the angular power spectrum associated to this. And then what you do is you bin the values usually. So you take bins and then you bin all the values into single dots there. And you compare the observed with the predicted, as you can see here in the figure in the middle. And when you do this, you can quantify how good your model fits the observed data, or how bad it fits it. So you can quantify this, and from there you can extract how likely it is for your parameters to take certain values. So you can get what is known as posterior distributions, which tells you basically the likelihood of your parameter taking specific values given your data. So here, for example, I've done a small little plot, which is in black, the estimation of the posterior distribution of the omega k parameter, which is the curvature parameter. This symbol represents curvature. If it's 0, it means this flat space, there's no curvature. If it's negative, it means we live in a spherical, positively curved space. If it's positive, it means we live in a negative, hyperbolic kind of space, the one that looked like a saddle of a horse or a Pringle chip. And we see here, for example, that at the peak of this black curve, we see that it's most probable and it gets wider, so some variability, and it's centered around 0. So what this tells us is that it seems like the curvature of space is flat, which isn't at all trivial. It's not to be assumed as something that would be expected. And in red, we have a more renowned and more well-known result from the Planck mission, the 2018 Planck mission. And they've combined actually some results that they got with other models or other predictions from other observations. So then sometimes what happens is your model isn't enough to constrain your parameters. There's some variability or ambiguity, and you need more types of observations. You need to observe reality in different angles or different ways to then finally constrain your parameters to a tighter region. That's what ends up happening. So just to wrap up things, what we've done now is we've briefly, I think I'm just in time. We've briefly looked at the cosmic microwave background. We've gone over some of its characteristics, properties. We've looked at some of the parameters that we could fit, in particular curvature. And we've also looked at how more or less a data analysis project would look if you did CMB data analysis at home. And that's it. That's been it. Thank you very much for listening. And it's been a pleasure to have this opportunity to talk to you all. Thank you.
Thank you very much, Raul. Do you mind just stop sharing the screen?
Of course, yeah.
We can see you a lot better. In the meantime, could you all please just put your questions in the Q&A? Any questions you have for Raul? We're going to, well, maybe Ashley wants to throw a question too. I want to throw 2 questions at you quickly before we dive in. I find this so exciting what you've done. Thank you so much, Raul. That was the most incredible,
Uh,
beautiful lecture because it's such a complicated subject. Well done. And
Thank you.
congratulations,
Thank
especially,
you very much.
you know, at your level, you're not yet at a PhD where you can give things so clear that are so complicated. So congratulations. Well done. Let
Thank you. Thank you.
two quick questions. One thing that always fascinates me, because of course, you're looking at the observable universe, right, with its certain radius, but in fact, we don't know what goes on beyond it. So, I mean, I know this is very speculative, but it's something that fascinates me no end because I just love looking out at the universe.
Yeah.
It's always what's beyond that, what is beyond the things that we cannot see, because the curvature of the universe could be anything beyond that, right? Or what's your
Yes. Yeah.
comment on that?
Yeah, well, again, as you mentioned, I'm not an expert. I'm still quite at a lower level compared to other people that are on PhD. It's very common or very possible that the universe is so big that even though we measure a flat space, it may be the same as here on Earth. We look at Earth and it looks flat, and then it just turns out that the universe is way bigger than what we expect it to be, and that
And
locally
it could have any
is
curvature
actually,
beyond that, right? Because
of
we could
course, yeah.
measure it, obviously, right?
Yeah, it's quite a humbling field because
Yes.
compared to other fields where you can have power on your experiments, we're just dominated by the large scales of cosmic time and space, and our lives aren't compatible with those scales. So the amount of phenomenology that happens at that scale is just not as easy to treat. Yeah,
Exactly. And the second question is, there's so much coming in now with machine learning, AI, neural networks, and so on. So what's
yeah,
your perspective? Because obviously this takes a lot of compute power, right? So what is
yes,
your perspective, going on into theoretical physics, especially the area that you're going in? What's the role
yeah.
going to be there of machine learning?
Yeah. So then that's a great question. A new direction which I'm now maybe going to take the project in is actually by implementing artificial neural networks. And I've noticed during this project that a bottleneck in the whole analysis of the data is in the generation of theoretical curves of the angular power spectrum. And sometimes this bottleneck can make your computation times increase to a point where it's just unfeasible for your computational power that you have accessible to you. So then um, one area that many people are looking into is in using neural networks to have fast code that can generate angular power spectrums or theoretical predictions given parameters. And these kind of models or trained neural networks obviously have to be trained on data. And this, for now, I haven't seen many models that are trained assuming non-flat space. So lots of them assume that curvature is zero, and then are trained on a data set that has other parameters that vary, but assuming a flat space. So then, for example, if you wanted to use these neural networks for fitting the curvature parameter, you wouldn't be able to because you'd be going outside the domain in which these neural networks were trained. So you've got to be careful with these tools because obviously they are good at what they do, but within their domain. So yeah, that's one
Very, very
aspect of it.
interesting. Thank you.
Yeah.
Ashley, do you want to add any questions?
No, you practically asked the questions I was going to ask, but we do have a question in the chat for the webinar for you, Raul. And one of them
Fantastic.
is, the question is, what are the tangible consequences of the flat cosmos? Do we know why it ended up flat?
Yes. So then I was actually thinking of sharing the screen and showing everyone an applet that's quite good. There's very good software or websites where they explain to you the consequences of the curvature. It's a very fundamental question in cosmology, and it determines the overall evolution of the cosmos uh, in the future. So it's a very, very fundamental question, and it has to do with the density of energy in space, and depending on if it's a critical amount or if it's more than that or less than that, you get very different behavior. You can have a big crunch, what they call, where all space contracts again. You can have a big rip, I think I've heard, where everything flies apart, and you can have other things in between those two extremes. There's a good applet that I was going to share. I may share in the chat the link if I can. And it's basically a good place to start because it shows you how, by tuning certain parameters, for example, for example, here I can see the amount of cold dark matter, the amount of dark energy, the amount of atoms in the universe. By varying these things, you get a different power spectrum. So inversely, you can, given a power spectrum, you can infer what does that mean on the universe content, if you like. I'm not sure if that answers your question perfectly, but I will send now the link through the chat so that everyone can play with this applet.
Anybody who wants to ask questions? Yeah, or actually, you want to take that up? So they're putting it to the webinar chat at the moment. Someone, so try and put it in the Q&A, but anyway, we're looking on both. Do you see that one, Ashley? Do you want to ask that one? Or
Oh, this one. Are there any opportunities for doing citizen science here?
that's a good one.
So in this field, I guess they say, I would not be able to answer you there. I would rather not give you a wrong answer than
Yeah, I think the question is very relevant because, in exoplanets, obviously, there's a lot of space for citizen science. That's where it's coming
yes,
from. So,
yeah.
Can we help measure the triangle?
Yeah,
Something like that. That's a difficult one.
I think machine learning in general is quite I was telling you before earlier, Christian, that I was interested in this kind of avenue of investigation because
Yes.
it allowed for novel things to be done, which don't necessarily have to be very complicated. So at a citizen science level, which is similar to my level, you can be part of a project that you do more or less grasp and understand, and at the same time be part of that project which is novel and new. So maybe looking into machine learning, maybe algorithms, maybe that could be a way of finding new things. I'm not sure. I don't feel like I'm completely suited for that question, and I don't want to give you a wrong answer.
No, that's fine. That's fine. It's good.
Yeah.
It's good. I mean, is there anybody else who wants to ask a question? Oh, here we come. Here. Ali's asking another question. Do you want to take that up, Ashley?
Yep. So we have the next part. The second part of my question was, can cosmology physics explain why cosmos is flat?
So the way we usually tackle this is we look at the curvature, we see it's flat, and then from there we extrapolate what's the content of the universe. So we can tell how much dark energy, how much dark matter, how much normal matter there must be. I don't think dark matter, well, it's very well known that dark matter and dark energy are not well known quantities. So I think that must be probably like where our understanding is right now. The main issue now is understanding, now that we know there's this quantity that must justify the flat space, how can we understand this quantity? How can we measure it? Can we see it in other ways, etc.? Yeah, we don't say first of all, we've got dark energy and dark matter, and then we say, well, then the universe must be flat. It's more like, like crap, we just realized it's flat. Okay, so then there must be something that makes it flat. Yeah.
Awesome. We also have another question for you. These questions are coming in really well, and they're some pretty good questions. So we've got one from Paul. After the influence of the Milky Way has been removed, are there any
Yeah.
other spots in the CMB associated with any visible objects? That is, are some of the high temperature regions actually nearby galaxies, or is this also already
Mm.
cleansed?
Yeah, that's a good question. So then, yeah, I think, for example, the Magellanic Clouds that are visible in Australia, actually, I think those are quite bright and appear in the CMB, but they don't appear as hotspots. They appear as blurred areas. So, of course, this depends on the filtering method that has been, or algorithm that has been applied to the map. What I used was maps that already came somewhat cleaned already. In specific, the 2018 Planck CMB maps have done an incredible job at removing all the foreground emissions. And there's some areas that are blurred out. They don't appear as hotspots. They more appear like blurry images. I could show you a picture if I had the time. But what you do with them, once you identify them, or once you choose how much you want to trust your data, is choose a mask. And a mask basically is a function that is on the sphere again. It has zeros and ones, and you put zeros wherever you don't want to look at the map. So if you see an area that's blurry that you don't trust, you just multiply that times zero, and it's not going to affect your overall predictions. And what you end up is with a CMB map that is zero everywhere you don't trust, and then you multiply it by one everywhere you do trust. So you keep it the same everywhere where you think it's actually the CMB. And from then on, there's more analysis that has to be done because there's some subtleties by doing that. But when you're doing harmonic transforms, multiplication in real space is a convolution in a harmonic space, so you have to deconvolve. There's some subtleties, but yeah, you essentially mask, to use a window function to cover up all the areas that you don't trust.
Good. Actually, there's some more, I think, coming. Do you want to read some more?
Yeah, so we've got, I'm just trying to see who has come first in
Huh?
there. So,
I
all
think
right.
Peter Laden is the next.
Yeah, I
Yes.
think Peter's the next one.
Mhm.
Yeah, so we have another question, which is, given the enormous amount of data to interpret, is it possible to create a subset of the data, limited amount of data across some fixed points, and then build a model around that?
Yes, so that's a good question. So the way when you take the harmonic transform, a spherical harmonic transform, sorry, um, uh, you can't, well, you can take it in a small region, but usually it will affect it'll bias your estimations. So your estimations will be better if you take the whole sky. In fact, what was done historically was there was a survey of the whole sky, and then the resolution wasn't that high. They then did a smaller survey just in a focused region of the sky called the boomerang survey, and they realized there was much more resolution to look at. So then they did, as a consequence of that, they did a whole survey of the sky this time with more angular resolution. And I think the key is to have all the sphere. If you cut the sphere in half, you are affecting, again, when you go to this harmonic space, you're doing convolution. So you do a messy operation. It's not as innocent as it may seem. It may seem innocent to just cut the map in a small chunk in real space, but when you go to harmonic space, when you do the spherical harmonic transform, that operation isn't as innocent, and it actually affects all across the angular power spectrum. So it's a delicate issue. I'm not sure. It's not trivial, that's for sure. Yeah.
Awesome. We do have an additional follow-up question, and I believe that seems to be the last question. And the additional question is, this could help to learn. To let AI learn more about the model without having the system collapse on itself because of the amount of data and gradually getting to better results. So do you see the possibility of AI coming into this?
So yeah, AI there's already neural networks that are used now to do these analysis. So again, you need to output predictions given a set of parameters, and there's already neural networks that are trained and available online that you can use to get these predictions given a set of parameters. I'm not sure if the question, I'm not sure if I'm answering the question right. I'll
I
try and
think
see if I
I
can read it.
I think Raul, what he's getting, I know what Peter's getting at. So he's getting at training neural networks. That's basically what he's getting at. So he's saying because there's so much data, it would flood the neural network. We take a subset, a subset to get to get some good response initially, and then increase the data, sort of feed it in gradually instead of plunging it all into one. That's
Yeah.
I think.
Okay. Yeah. So usually a common practice in machine learning when you have neural networks is you have a data set and say you've got 100 data points, and what you do is you split the data, you partition it into a training set and then an evaluation set maybe and a test set, and generally the more data the better. So neural networks don't struggle that much with having too much data. They normally do better with more data. You want to have good data, of course, but usually the main problem is overfitting. So as these neural networks are they've got so many parameters, they're very flexible. It's like using you try and interpolate a set of dots with a very high order polynomial. So it's like very, very easy to overfit data. So then you normally need to impose other constraints for it to be more robust and not as varying. But yes, of course, yep. So then what you'd do is you wouldn't feed all the information because that would lead to overfitting. You'd want to like feed maybe 70% of your data set, and then the remaining 30%, you could use it, for example, for testing it. And if you see that it does very well, if your neural network performs very well in the testing, but performs very badly in the opposite. If it performs very well in the training, very badly in the testing, it would indicate overfitting. And by doing this split, you can detect that and you can solve it.
Good answer. I think that's what Peter's looking at. Yes. Good.
Yeah.
Mm-hmm.
Perfect.
Good. I think then we can close today. So I would like to thank everyone, first of all, for attending and all your interest, which is great. I mean, we spent a lot of time on the questions, and of course, our speaker, Raul, fantastic, really. And good luck
Thank
in
you
the
so much.
Thanks for actually bringing you here on board. Really appreciate it. A good job, Ashley, really nice. And we're going to continue the webinar series. We'll get more speakers. We'll get this flowing again. We've been quite silent for a year, I know. We've got some interesting ideas coming up. So please stick with us and thanks for all your support. And we'll see you soon, everyone. And have a wonderful weekend and clear skies. It's new moon. Okay. Okay. Thank you. Thanks, everyone. Bye.
Thank you.
Okay. Thanks. Bye.